Okay, this is Chapter 7. This is Section 7-1. This is recording number 3. Okay, so at the end of the last tape, what I was trying to get at here is that if you have something like this, x bar plus or minus this, okay, then there's a 95% probability that mu plus 1.96 times this contains x bar. Likewise, there's a 95% probability that the interval specified by this will contain mu. So it's kind of a reciprocity thing here, right? In other words, mu plus 1.96 times this and x bar plus 1.96, they will contain each other. This will contain x bar and this will contain mu. Okay, so as he says here, he's going to show that to us later. Okay, stated another way, if this is your interval, mu is between x bar, take away this, and on the right hand side, x bar plus this. So what I would urge you to do is write that out in the form of a number line. I think it would be more clear to you. Okay, what we're saying is that there's a 95% probability that this interval, here is on the right hand side, this is on the left hand side, will contain the mu. That's what it's saying here. Now we just kind of arbitrarily chose this 1.96, arbitrary in the sense that we arbitrarily chose the 95% confidence interval. It doesn't have to be 95%. It could be some other confidence interval. It could be the 99% confidence interval. If you choose 99% confidence interval, instead of using 1.96, we use 2.58. Okay, and it's all based on these cartoons that I showed you in the last video. Okay, so this symbol z sub alpha over 2 is used in the general formula. That's what we're going to use down here, because otherwise we'd have to write down a formula for every single confidence interval or every single confidence level that we wanted. We'd have to have a different formula. Well, that'd be kind of stupid, right? So what we do is we say, without loss of generality, this is the z value that we're going to choose. What's the z value? It all depends upon what the alpha is, and the alpha is the allowable error. So if you're allowing yourself, if you're saying you want it to be 95% confidence level, as an example, if you want it to be 95% confidence level, that means that you can be wrong. Alpha over 2, okay, it's 5% over 2, it's 0.025. So it's 2.5% of the time you're going to be wrong. So an alpha of 0.05, alpha of 5% means that 2.5% of the time you're wrong over here, 2.5% of the time you're wrong over here. It's always going to be this half. You're going to be half of being wrong is over here, half of it is wrong over here. Okay, so I agree that this formula is very formidable. Okay, it looks bad, but once you use it a few times, I promise it will not be as bad as it looks. Okay, so now this margin of error. Okay, the margin of error is the maximum likely difference between the point estimate and the actual value of the parameter. So it's kind of a funny definition. So the margin of error is this right here. This z value multiplied times this standard error. And don't blame me for this language. That's just the way they call it, okay? So this is instead of calling this the standard deviation, they call this the standard error. So it's the standard error times this appropriately chosen z value. And the z value is chosen based on what you want your alpha to be. So it's like a dominoes. Once you choose what your alpha is, then you choose what your alpha over 2 is. It's half of what the alpha is. Once you chose that, then you choose your z value. And once you have your z value, you multiply the z value times the standard error. That gives you the margin of error. Okay, so this guy right here, this right there, is called the margin of error. So the typical scenario is you'd say, well, the average age here is 22 years old plus or minus 1 year. Okay, so that your margin of error is 1 year. So that's a kind of a easy way of thinking about it. It's plus or minus a certain amount. How much do you think you're wrong? And how confident you are is the confidence level. Okay, so here's the assumptions. We always have to assume there's a random sample. If it's not a random sample, we're just, whistling Dixie here. The sample size has to be greater than or equal to 30, or the population is normally distributed. And if it's normally distributed, we don't care what the sample size is. Okay, I'll let you guys read that. And there's a rounding rule. I'll let you read that as well. So let's see if we can come up with something here. Let's see. This may not be the most exciting example, but it kind of illustrates the point. Okay, so we want to find out how many number of days it takes to sell a certain type of a car. Okay, we have a random sample of 50 cars, so our N is 50. Okay, it had a mean time. Okay, so our X bar is 54. It had a mean time on the lot of 54 days. And assume the standard deviation is 6 days. Standard deviation is 6 days. Find the best point estimate of the population mean and the 95% confidence interval of the population mean. Now, as I've mentioned, these examples are metaphors. It would be very easy for us to come up with a slightly different set of constraints here. I think that would be a lot more relevant to you, but it would just require so much more additional discussion about the underlying issues. Like, for example, right now we're going through this pandemic, right? Well, suppose instead of talking about how many days it takes to sell a car, suppose we're talking about how many days it takes from the first day that you're infected or you show the antibodies to the last day where there's no, see that right there I'm getting all screwed up. But I'm going to leave this in the tape just to illustrate what I'm talking about. We have to go through so much discussion about biology and medicine in order to use something other than selling a stupid car. But as an example, if you were to consider how long does it take to be considered virus free, where your virus load is less than some sort of an arbitrary level that the doctor chose. Okay, well, we could discuss that, but we'd have to discuss viruses. We have to discuss all kinds of things before we get into it. So don't think this is irrelevant or boring just because the examples are boring. We can use this in all kinds of contexts that would be a lot more interesting, but we just don't have time to go into all of the background. So that's the last time I'm going to mention this. I hope I've convinced you that these examples are metaphors. They're not intended to be that interesting. They're just intended to explain to us what the heck is going on here. Okay, so we got all the information we need. Okay, what we're looking for is the best point estimate and a 95% confidence interval of the population mean. Well, the best point estimate is always going to be easy. It's always going to be the X bar. So X bar is always going to be the best point estimate. The interval that we're going to be looking for is we're going to say, well, the mean of the population, in other words, the mu, is somewhere between X bar, which is the best point estimate. So the best point estimate plus the margin of error, and the best point estimate subtract the margin of error. So it's in this interval of X bar plus or minus the margin of error. Here's the margin of error. Well, now it's just a matter of plugging things in. The sigma and the square root of n, that was given to us up here. The sigma, they told us, was 6 days. N is 50. The square root of 50 is whatever that number is, okay? All right? So the only thing that has any difficulty whatsoever is how do you choose this number here? How do you choose the z alpha over 2? Well, that just comes from a little bit of experience in looking at the table. Plus up here, I believe he does give us the common ones. The common ones right here. For a 90% confidence interval, the z sub alpha over 2 is 1.65, and so forth. So you can write that down somewhere and memorize it, or just have it on your cheat sheet, or whatever, however you want to do it. Okay, so we get those numbers. The 1.96 gets plugged in here, so it's 54 plus margin of error, 54 subtract margin of error. Mu is between those two guys. So you do the arithmetic, use your calculator, of course, and so now what we say is mu is between 52.3 and 55.7. Or we could say it is 54, that's the x bar, 54 plus or minus 1.7. And the 1.7 comes from right here. Okay? So what do we say at the end of all this? What we say is, I can say with 95% confidence that the interval between 52.3 and 55.7 days does contain the population mean, and that's based on a sample of 50 automobiles. So I can say that. I'm 95% confident. If you did this experiment a bazillion times, 95% of the time, you would find mu in here. 5% of the time, you would be wrong. So if you're talking about a medical concept or medical context, you would say the population mean is between 52.3 and 55.7 days. That's my confidence level is 95%, but 5% of the time I'm going to be wrong. Okay? All right, so we got the same idea here, number of patients. They can see average of 18 patients per hour, get a certain standard deviation. You get a random sample of 42 hours, okay? 99% confidence level. Okay, so do we have everything we need? We have the standard deviation. That's my sigma. Okay, that goes in here. I have a random sample of 42 hours. That's going to go right here. That's n, square root of n. And the 99% confidence interval, that's going to give me this guy right here, which you can look in the back of the textbook. You can look in that table to find it, or as I mentioned before, it's actually given to you up here. It tells you what it is. Just saves you the trouble of looking it up if you write it down somewhere. And I can tell you, if you were doing this for a living, you'd have those memorized, or you'd have them written down somewhere. Okay, so now it's just plugging it in. So you're 99% confident that the mean number of patients that the center can care for in 1 hour is between 17 and 19. Okay. Okay, he talks here about another way of looking at it. I don't see where that adds anything to it, so I'm not going to go into that. I do want to talk here about sample size, though, because it's very, very, very important to know about sample sizes. Here's a comment about using the computer. Please make sure you read that. Okay, now the sample size. What he's talking about here is the minimum sample size. Okay, so it's a very important topic here because we want to know how large of a sample is necessary in order to make the estimate. Okay, it's a very important topic. So I'm almost out of time on this video, so I'm going to talk about that next. But I want you to just see that there is this natural segue, S-E-G-U-E. S-E-G-U-E, segue, means a transition. There's this natural segue here from talking about, talking about the interval estimates. I'm trying to find it here. I'm sorry. Okay, so here's the interval that we calculate. We calculate the confidence interval, and we have an n. The corollary to that is the question, how big of an n do you need? See, they're just giving us the n, but if you were designing this experiment, you would have to decide that for yourself. So whatever confidence level you want will dictate how big the sample size has to be. So we'll talk about that in the next video.